when we do commercial projects, we put a map next to that readily accessible solar disconnect, denoting where the main service panel is. Uh, you know, it's code requirement. Um, with our disconnect switches, there's a few different kinds. I've I've started to find some disconnects that are for smart homes that can disconnect remotely. The main thing when you're looking at like machine operable, remote operable disconnect switches is to qualify as the actual disconnect and not like a auxiliary or secondary disconnect. They still have to be manually operable. That's kind of a difference between U.S. electric code and in other countries. Is we tend to err on a more mechanical and bulkier because of that disconnect switches, whereas in other countries they go more for digital controls and making their service panels smaller because of that. Um, the minimum rating of a single family home is 100 amps. Here we get into some additional rules for circuits that are over 600 volts. In a commercial system, you're commonly going into 1,000 volt system, and even in utility scale, they can go beyond that. And so once you get over 600 volts, the disconnecting means are required to be up and down. And you think about the breakers in your electric service panel. Let's say you land a solar array on your electric service panel. That breaker is usually going left to right. So, that's where, again, where like a local jurisdiction may want to have that knife switch disconnect because that knife switch goes up and down. You can argue to them that the breaker switch on your service panel is is the disconnect, and they might say, well, it doesn't constitute the up and down requirement. That's for over 600 volts. Here we have a substation requirement that says, you need not just a sign that says, where the other disconnecting means are, but an actual single line diagram that identifies at each point of connection to high voltage. And so on our commercial systems, we also put a single line diagram at the solar disconnect or within the inverter room. Not to say that your inverter room is a substation, but it is also a common AHJ requirement, kind of originating from earlier sections in National Electric Code. So now we start to see feeders versus services. And so it says a building or structure shall only be supplied by one service, except for backup power, emergency power, parallel power, which a solar array or a battery would be, even if that solar array or battery is not a backup power, emergency power, or standby system. Or if you get special permission or your building is particularly large, you can get multiple services coming into that building, like multiple big bulky transformers feeding that building. It says one building or structure should not be supplied through the interior of another. And so then we have to determine, well, what's considered outside a building? So if you have two buildings next to each other, how can you route the power lines from one building to the next? And there's rules and regulations that govern it, such as if you have you can run them under your concrete foundation. so long that there's 2 inches of concrete. Or it's common to have let's say you have a basement. If you can encase those conductors in concrete, um, that's another that's another way to get around it. Um, Here's one that is pretty common. Conductors in the same raceway for electric services, except for your electric grounding conductors. And then it says also, except for load management conductors, are not allowed in the same raceway. So let's say you have a solar array or a battery bank and some power outlets. You're not allowed to share the same raceway for your power cables along with your solar array cables unless it is for load management control. So where would that might be? Well, that might be if you get a shielded Ethernet cable to run your communication systems between your inverters, so that your inverter can, the new kind of standard allows, let's connect our inverters to the internet so that the utility presumably could scale back your production. Or over in New Hampshire with Green Mountain Power, the utility will actually have online access to your Tesla Powerwall battery banks, and they provide an incentive for allowing the utility to dispatch the power in your battery when needed. It can be kind of annoying to run an extra conduit just for your internet cable. And depending on what Ethernet cable you select, you can now run that in the same conductors as your solar conductors. So here's yet again another call for a raceway seal when it comes in from underground. Really, it's whenever it goes through temperature differential. You want to seal that raceway so that you don't get rain occurring inside of your conduit and raceways just from the moisture in the air, the humidity condensing across that temperature differential. And just like feeders, we see similar requirements for services. Feeders and services are pretty similar to each other. Those service conductors should be insulated, with the exception of your grounded conductor. If you're using like a equipment ground conductor, it's common to use bare copper. Underground service conductors, not smaller than number 8. That would be for a very small sub panel. So then we get into a mention of spliced conductors. So that's kind of interesting because let's say you're pulling your cable and you messed up your material estimate and you're a little short. So the question becomes, when can you splice your service entrance conductors? And so what it's saying is we're going to kind of punt that into a later section, the section's 300. So we're going to get there in a minute. So one set of service entrance conductors going into the building, unless you have buildings with more than one occupancy. So you can have your transformer on the side of the building, and then coming out of that transformer, you can have multiple sets of service entrance conductors. Again, their disconnecting means should be grouped together, and every time you get more than 6 switches, you need to have a main switch. You say, well, okay, but the six handle rule doesn't really, you know, apply in the sense to your standby power and solar breakers. You know, if you have a main lug only panel that feeds six separate distribution panels, and then you want to tap on the supply side a solar array or a battery bank, you know, that does not mean you have to upgrade that panel to a main. You know, where this might come into play is often you'll have a service panel that's integrated into the meter base called a combo panel or an all-in-one panel. And that usually that allows you to, you know, feed a, you know, auxiliary garage or some exterior power outlets, and you don't have a main breaker on that combo panel. You know, the panel will just, you know, go into the inside with a couple of breaker slots on the outside. Once you get more than six breakers on that panel, you need to have a main. So let's say your combo panel has six slots available for breakers and you've used them all and you want to add solar to it. You know, that would be a good use of a knife switch disconnect that would be separated from those six handles and then tapped onto the service entrance conductors ahead of that. And that would not count towards that six handle rule. So we see, like before, like with feeders, the ampacity for service conductors is, you know, 25% larger than the continuous load. And then we have an exception that says grounded conductors not connected to an overcurrent protection device shall be permitted to be sized at 100% of the total load. And so that's where you start getting into an undersized neutral. So remember that the neutral wire is a grounded conductor. At your service entrance, it's connected to ground. You know, it's carrying current back from the circuit. You know, so it is a current carrying conductor, but it's not, you know, tied into your breaker. It's tied into a grounding bar or a bonding bar on your service panel. And so remember with our breakers, you know, we don't want our breakers to trip when we hit our maximum load. And so we upsize the conductors by 25% and we round up our breakers to be a little bit larger. So when we hit our continuous load, they don't trip or burn up our wires. You know, the neutral conductor is allowed to be sized to 100% of the load when it's just landing on that bonding bar in your service panel. So that's where your neutral conductor may appear smaller than your, you know, power conductors, because your power conductors are upsized by 25%. Your neutral conductor needn't be. Minimum ampacity of the conductors shall not be less than the rated service disconnecting means. You know, so there are exceptions for getting around the upsizing of 25%, but under no circumstance would your conductors be rated for, you know, less than what the power than the breaker that they're supplying. I guess one thing that's interesting about this is, you know, whereas our load breakers, we're rounding up to the next breaker size. You know, what this means is that our service entrance conductors, we're not rounding up. That rating of the disconnecting means shall be rated for the ampacity of the conductor, which means you're really kind of rounding down compared to the ampacity rating of the conductor. We'll see that appear a little bit later. So the neutral is routed with your power lines. inside the same raceway, not going along the exterior of the raceway. And so now we should have a little bit better understanding of what's going on with our let me pull up my pencil. There I hit it. So now we should be able to understand what's going on with this one-line diagram a little bit better. So here's our solar array, and our equipment ground conductor is connecting to our metal frame and connecting our metal frame to ground. Here we are connecting to ground, and we have our positive and negative going into our inverter. And here's our neutral. And notice, this solar array is on the load side. It's not on the supply side. So we're not, bonding neutral to ground and, our box or our disconnect switch. That neutral is being carried through all the way to, our main bonding jumper, which is connected to ground in our service panel. And so we may connect our ground to ground on the DC side, or you can carry it through to the AC side. There's different rules for that. The main rule is to make sure that if your DC ground conductor is larger than your AC output ground conductor, which is rare, but you might have a very large solar array on an undersized inverter and run into a case where the ground conductor size for the solar array is required to be larger than the AC output. If you're going to carry through your ground from the DC side through the AC side, you need to make sure you're using the larger of the two sides for the AC side. So how do these breakers work anyway? Basically, the electricity produces heat, and as that current heats up, it's going to pull the breaker open. A ground fault detection circuit is a little bit different. They're actually monitoring the flow through the circuit. Similar to how an electrician can clamp around a conductor with his clamp meter and through induction monitor the current flowing through it. Ground fault protection circuit has an additional monitor so that it can monitor flow that is not so large enough to cause the breaker to open up due to the metal warping, but instead catch smaller ground fault currents. So they're more expensive, and they'll trigger, not just when you're at your maximum ampacity, but if you have a little bit of current, contacting, let's say you pulled a cable through your conduit and you weren't doing things in a workmanlike manner and you scraped the cable jacket. So now there's some exposed conductor touching the side of your conduit, causing a ground fault. That grounding will be carried back to your service panel. It's bonded to your neutral. And so inside this breaker, along with the neutral, it's checking for any stray current going through that neutral, and if it and will trigger it. Let's get into a different definition for listed. So this is for the hobbyists, the do-it-yourselfers. You may look at the price of some of this balance of system material, and it can be quite expensive. You may start looking into, things like marina batteries. And say, okay, well, I use this particular disconnect switch on my, Marina battery. Can I use it on my solar array? Listed says it's two things. One, there needs to be an organization that has approved that device for use. So, there's UL, Underwriters Lab, there's CE, there's a non-USA listing called ETL, and sometimes you might get a foreign inverter that has like a ETL listing, and they'll say it also complies with the UL standard. So you say, okay, well, is it a listed device? Yeah, if you have a CE mark or an ETL mark, but not a UL mark, it is a listed device. May not be acceptable to your local authority having jurisdiction. They might say, no, we need a UL listed equipment. So that's something to check out if you're using kind of foreign parts that aren't UL listed but have other listings, say in Europe. And then the listing either says it's identified to meet a standard, or it's tested for a specific purpose. And so what that means is one thing that that's common is you might want to perform a wire splice, and you can find these little splice kits at your local box store. We'll pull up in a second. But what we're about to look at is a splice kit. And so here's a terminal block where you have one conductor on one side and another conductor on the other side. And you put this shrink tube around it, and you heat up the shrink tube, and you wrap that shrink tube around your conductors. So this is for rated for direct burial, high temperature. You say, well, can I use this to splice solar conductor together? Well, you go and look at the ratings, and while it might work, it's not listed for solar purposes. It's listed for direct burial splicing. So, you'd have to beware that you could fail inspection for using a improper splice kit inside of your conduit. The splice may be allowed, but is what you're splicing, terminating, performing the splice with allowed? And so, that's buyer beware if you're borrowing from, just going to Home Depot and trying to piece together what you need to install your system. And you might be finding some Marina disconnects or some, splice kits. They may not be listed for the, environment that you're installing your solar array in. So we have different ways to create our raceway. One thing I'm thinking of is I have this inverter that sits on the ground. It's a SMA inverter. It's designed just to plant right on top of the rooftop. And the DC goes in the right side of the inverter, and the AC goes in the left side of the inverter, but the design has the inverter sitting between two different subarrays. And so you get this kind of, I don't know, it's a little puzzle. Here's a box, and the DC goes in one side, and the AC goes in the other side, but you have a solar array over here, and a solar array over here. And so you're routing your DC into the DC side, and then you're routing your DC into the DC side, and your AC needs to kind of come out and jump over the DC side. And so we're using EMT conduit for this, and EMT conduit, doing small bends in EMT conduit is kind of difficult. So we use flexible metal conduit for our in this case, we're doing a supply side tap. It's a service entrance conductor. So we're doing short sections for that. Cable tray rather than EMT conduit is a more professional way to go. It's also more expensive, which I imagine is why this client specified EMT instead of cable tray in their bid. So service entrance conductors can be spliced, but there's rules governing those splices. Splicing needs to occur inside a box or a conduit body for certain cables. It says, if you're using conduit or tubing, metal clad cable, AC cable. We're going to talk about different cable types in a few slides. And so where can you splice? You can splice in, inside gutters, inside raceways. There's certain cables like this mineral insulated cable. It's a cable with a super strong cable jacket that's allowed to be spliced outside of a gutter or raceway. Your solar cables. We have solar cables are rated for being outside of conduit, and we have a particular connector that is also listed for splicing solar cables, and it's called a MC connector. And one example would be the module to module connection on the rooftop, where you're just plugging in the module to the next door neighbor. That's not inside of conduit. And so we have a splice box that is, I guess you could say that maybe the housing of this is the conduit body, but it's a solar specific. It's a way that you can splice or connect two solar modules together, or the end of your solar circuit to your home run, without going into conduit or a box to perform that splice. So here's another definition of fitting, and this is, the keeping the electrical balance of system terms consistent is something I always have to deal with when I have kind of new hires on the job site. Fittings is a term to describe all the different kinds of connection points between conduit and electrical boxes. So a conduit to conduit connection, or a conduit to a box connection. We have little pieces like lock nuts and lock nuts that help tighten down a connector to the box, a bushing that prevents the cable from rubbing up against the metal, and provides a little bit of insulation from the metal. All these are called fittings. Fittings perform a mechanical rather than an electrical function. So we have how how do we protect our service entrance conductors? So, one common kind of design for solar ground mounts is they say, well, do I have to run conduit from the ground mount all the way to my point of connection and then pull cable through it? And that can sound really nice to the owner because it's like, oh, okay, well, if I want to expand the array, I might want to upsize my wire. And so, I might have a really large conduit. Um, Pulling cable through conduit over long distances is not easy. And the concept of reusing the conduit is not easy either. I mean, if you have cable already in that conduit and you want to pull another set of cables through that conduit, even if you have the empty space available, the cable that's already inside the conduit is going to interfere. You're not going to be able to pull cable through conduit when there's cable already in it. I had a client who was insistent on putting conduit between his battery house and his house, but his battery house was uphill of his house. And basically all he was doing was installing a drainage system that drained from his battery house directly into the foundation of his cabin and increasing the labor cost to boot. Now, you don't always need to have your underground cable in conduit. It's if you're like running your cable under a road where you have heavy equipment driving over the road on a regular basis, then you would be concerned about the weight of those vehicles pushing down sticks and rocks in the dirt and nicking your wires. That said, even if you could still have a tree root system disrupt your direct buried conduit, or not direct, your underground conduit, and if your conduit's being busted up by dirt and tree roots and rocks and other things, it is going to provide a little bit of physical protection for the cable that's already inside that cable, but it's not going to be reusable over and over if you want to expand your system down the road. What would be smarter for an expandable system is when you're digging your trench to put in an empty conduit rather than a full conduit for future use. And so I'm more of a fan of using direct burial rated cable and doing exactly that, just throwing it into the trench and covering it, at which point you put down a warning ribbon. So if people are digging in that area, they're going to cut into the warning ribbon before they cut into your conduit and kind of signal to that trencher, hey, there's something down here. Then again, individual open conductors within 10 feet of grade or exposed to physical damage, individual open conductors shall not be within 10 feet of grade or exposed to physical damage, with the exception of there's mineral insulated and then metal clad cable. So what does that mean? Well, we're going to talk about different cable types later, but it basically means that if you have conductors running, say, on the outside of your building along the wall, they need to be given physical protection, or you need to use a more robust cable that already has that protection built into the cable jacket itself, such as mineral insulated cable or metal clad cable called MC. It's they call it cable because the cable comes pre-packaged inside of it, and you get this metal wrapping that goes around the outside of it. You can buy the metal wrapping separately and pull the cable through the metal wrapping. It's hard to do. So they call that something else. They'd call that flexible metal conduit with cable inside, whereas the MC, the metal clad cable, comes pre-bundled. That extra metal jacket gives it a little bit more physical protection. So where do we put our mounting supports for service entrance conductors? It says within 12 inches of every service head or raceway connection or enclosure. So you need to support that conduit coming 12 inches out of your box. Then it says with intervals not exceeding 30 inches. And then other cables, like your solar home run cables, rather than your, maybe your inverter output circuit, are allowed to be supported with greater distances. So this, not knowing anything about electricity, this stuff over here, kind of ticks me off just because it looks so ugly. It's like, why are they doing all this with this extra cable so that it, looks like a little rat's nest up on your rooftop? Well, code requires individual open service entrance conductors to enter through the roof or the walls with an upward slant. Now, that's so rain that hits these conductors slides down and drips off rather than going into the building itself. So there is some method to that madness, or method to that rat nest. Raceways to drain. So we're exposed to weather. Raceways enclosing service entrance conductors shall be arranged to drain. So, we have from our battery house, this conduit running down the hill being focused at that foundation wall. Well, before we get to that foundation wall, we need to stop and make sure our conductors are moving upwards. Where we do this is when you're on a rooftop and you have your solar cables going into the rooftop. The rooftop's already slanted. If we have a junction box on the roof for our cable transition, we go into the bottom of the box at the bottom of the slant. So here we have a rooftop. We might have a little junction box, and usually I'm going to hide that underneath the solar array. So here's our solar panel, on some, being supported by some solar racking that goes, along the array. And so we're going to come into the underside of the box rather than the top of the box or the side of the box. We go into the underside of the box. If you're not using a box, if you have just, instead of this picture, if you have conduit coming up in the roof, you want to put a little 90-degree bend, you can get 90-degree fittings so that your solar conductors are coming at a slant such that they drain. So it says we're impracticable to secure your gooseneck or service head entrance within 12 inches of that service head because it might be sticking out of the the roof, locate that attachment within 24 inches of the point of attachment instead of 12. All right. Service equipment should be enclosed or guarded. So energized parts should be enclosed or guarded. Enclosed meaning not exposed to accidental contact. Guarded does not necessarily mean enclosed. And so I'm thinking about up on a rooftop where we have, a solar inverter, and on the side of our solar inverter, we have little plugs for our solar circuits. And our solar circuits are coming out of a raceway with a cable gland. And our solar circuits are coming out of this cable gland and plugging into the inverter. If that's a accessible rooftop where people are, I don't know, let's say there's a patio on that roof, that is an energized conductor that's not enclosed and not guarded. If the rooftop's not accessible, you could consider it guarded. And the inspector doesn't have to consider it guarded. And you can say, well, there's qualified service persons up there, but it says, well, hold on, if we have a roof hatch that is locked so that people can't get up there, if I'm putting all my batteries and components in a shed and I'm locking the shed, then I don't have to have the energized parts be enclosed so long as they are guarded. Which basically means you're locking out unqualified people from accessing that room or that location. We've already talked about what readily accessible means, either outside the building or inside at the nearest point of entrance of the service conductors. It's the local AHJ that requires the external disconnect. Again, we see the 6-handle rule reappear. So now as we're getting further and further into code, what we're seeing is some repetition. It says, we already laid down the fundamental theory for power circuits or feeder circuits. Now we're talking about a specific kind of feeder circuit, a service entrance conductor, and we're just reiterating that the rules still apply. So there's a lot of code where you're reading the rules in the solar section or the battery section, and they're just reiterations of what we saw for power circuits or service entrance circuits. And so here we have a ground mount solar array, and we have a distribution panel. And here are some subarrays going off to the side, and we have 1, 2, 3, 4 different breakers, and then a main breaker. This main breaker really isn't necessary. We could do a main lug only panel instead, since we can de-energize this with 1, 2, 3, 4 turns of the switch. Or we can put a single knife switch disconnect if we got rid of this main lug only. And this is since we're on the point here, your knife switch disconnects come in 2 options. They can be fused or non-fused. The question is, when do you have a fused disconnect? When do you have a non-fused disconnect? Well, actually, in this configuration, we don't need a main lug only panel. We don't need a main disconnect switch. We got our 4 handles here, and they all have their overcurrent protection. We're kind of, overkilling, maybe not really, making the best use of our money, although, the cost between a fused disconnect and a non-fused disconnect is not that different. You need a fused disconnect when you don't have a breaker providing overcurrent protection. And so it's common if you just have a single inverter and you want to tie it in to your service entrance, instead of having a service panel, you put a disconnect switch. So this is the inverter here, and here's our disconnect switch. Well, there's no overcurrent protection at that point. There's no overcurrent protection at that point, and so we would use a fused disconnect switch. If we already have overcurrent protection, then we don't need a fused disconnect switch. Not that you can't have it, it would just be redundant. And potentially, if it ever blew, you'd have to replace it before you could use your system again, whereas a breaker, as opposed to a fuse, is resettable. Then again, that resettability of the breaker isn't the best thing in the world, because breakers shouldn't trip for no reason. It's quite rare to come across a bad breaker as opposed to a ground fault due to poor workmanship. And so having a resettable breaker where the breaker trips and the client just goes and resets it, there's usually issues that need to be looked into and diagnosed and addressed, like loose connections. I'll just share one on my own. I had a solar inverter where here's our cable jacket and our little copper coming out of it. And what I had done is I stripped too much copper off. The copper was supposed to only be stripped off about a 1/4 inch, and I had stripped off a 1/2 inch. And then I landed it on my terminals. I had 2 terminals here, and I was getting a fault between my 2 terminals where the cabling was stripped too long. And so you might come across different inverter systems with different terminal blocks, and for some 1/2 inch is just fine and dandy, and for others, stripping off a 1/2 inch is way too much. Well, we had an arc fault, or actually this one was a ground fault, and it tripped the breaker. Well, then the client went and reset the breaker, and the ground fault continued, and it burned up the terminal block, and we had to replace the inverter. Whereas if it had been a fuse instead of a breaker, the problem would have occurred. And then you're kind of idiot-proofing the system, because it would force the installer to come back out there and replace the fuse and see what's going on before the problem got worse. But just beware of breakers tripping and you resetting them. They shouldn't trip for no reason. I had a client call me who's living off grid, and she said, the power went out to her house. And so I walked her through how to look at her service panel, and she saw that a breaker tripped. And she said, well, I was using both of my dryers from doing some laundry, using both of my dryers at the same time. It's hot down in the south, so I'm sure air conditioning was going. She's like, and I know I'm not supposed to use both my dryers at the same time, but I did, and the breaker tripped. Great. We know why the breaker tripped. Reset the breaker. You're going to be fine. It's when you don't know why the breaker trips that there's an electrical issue that needs to be diagnosed. Here's a 1 megawatt ground mount we did where we had individual inverters being wired back to a single service panel. And so what we did is we looked at the number of slots that we could tie in our inverters to, and it turned out our service panel had enough slots to tie in 1, 2, 3, 4, 5, 6 inverters. So we did not need a main lug only panel. I mean, we did not need a panel with a main breaker. If we had added a 7th inverter, we would have needed a main breaker on that panel. And so now you can kind of understand why, you know, a service panel with tons of breaker slots is going to have a main breaker switch, whereas you can find these smaller sub panels that won't have a main on it. Now here's a kind of an exception to that 6-handle rule. It says when you're counting your disconnects, if you have a breaker on that, you know, smaller sub panel that we saw pictured right here, and that breaker is for, you know, running a piece of monitoring equipment. So you have little current transducers that you put inside your service panel now to monitor current flowing through your service panel. They require power and put on a single pole breaker. Say that's not, you know, that's not what we're not going to count that as part of the 6-handle rule. You may have a surge protection device. You know, maybe a power circuit for a power operating disconnect. You know, those breakers are not considered to be important enough to count for towards that 6-handle rule. You know, we already talked about special cases, you know, grouping other supplies, you know, backup power disconnecting switches separately from your main. So then we have equipment connected to the supply side of a service disconnect. Now that's pretty interesting because, you know, here's your meter base and here's your main service panel where all your loads are connected. And what we're saying is there are cases where you can tap onto that service entrance conductor and put devices here instead of there. You know, that could be useful. Let's say you're doing a solar array and you're buying a American-made inverter that goes outside the building. You know, and I say American-made, but, you know, generally your higher quality inverters that are common to the U.S. market are rated for outdoor environments. I know a guy who runs kind of a dispatch office for a large residential solar finance company, and you know, he says, okay, well, yeah, you know, it's better for the inverters to be inside in a dust-free environment that's air conditioned, but I run a solar leasing company, and when there's a problem with an inverter, it needs servicing, I don't want it to wait around for the client to be home to service the issue. I just want to be able to send someone out there and service the inverter. That's a lot easier to do if the inverter's on the outside of the building. Well, your service panel might be on the inside of the building, but your meter is on the outside of the building. And so you might want to connect your inverter on the outside of the building. And that's pretty common. I mean, what I typically do is, here's my very crude house, and I'll put my solar array on top, and then I'll run some conduit through the roof and then out the soffit. And so my inverter's on the outside of the building. Being able to tap on to the service entrance conductors is convenient. So when can you do that? There's certain cases. There's only certain equipment that you can connect to the supply side of the service disconnecting means. The service disconnecting means being the main breaker on your service panel. So the current limiting devices like lightning arresters that will blow when there's a power surge, a meter base and a meter socket, disconnect switches for those meters, load management devices. Well, that's interesting. What are those? Well, they could be remote access breakers that disconnect service panels when your load is too high. Could also be a battery that pumps juice into the system whenever your building demand reaches a certain threshold, so that commercial buildings are being billed by demand charges. We talk about this in our commercial solar peaker class, but using solar and batteries to reduce the demand charge on a commercial electric bill, in many cases, is the most cost-effective application of solar on the market today. And it says the only And so other kinds of equipment that are allowed to connect to the supply side between the meter and your service panel are, fire alarm systems. I'm shutting down the building to work inside the service panel. I don't want to disconnect the fire alarm system to the school. Usually it remains, powered up. A standby generator if the grid's down. I want to switch on to a generator. I might have a transfer switch with a generator connected, and if I'm trying to power my whole building, it needs to go between the meter base and the building. Solar arrays are allowed to be interconnected on the supply side as well. So you can't connect just any circuit between the meter base and your main service panel, but you can connect certain things related to power generation, backup power, and energy control. Which is why if I have a meter base and a main service panel, and I want to tap on an additional service panel, and I'm tying in, power monitoring and solar arrays and batteries, I'll just call this an energy service panel because I'm connecting energy-related devices to it. This one's on the quiz. The definition of a short circuit current rating. Short circuit current is the current at your regular voltage, operating voltage, to which an apparatus or system is able to be connected without sustaining damage. So I look at my solar panel and it has a short circuit current rating. And so I might think that the definition of a short circuit current rating is like the maximum current that the panel could output on, the maximum. what short circuit is the maximum current that the panel could be. Let's say there's a ground fault and it has a short circuit. Let's say I take the two leads of my solar panels and I connect them together, or put them in a puddle that's connected to ground, and now they're ground faulting to ground. That short circuit current rating is the current rating that can be designed into the system where nothing's damaged when that happens. And so if my solar array is ground faulting and it trips the breaker, I can go identify the ground fault, fix it, turn the breaker back on, and my equipment hasn't burnt up, my wires haven't burnt up. It's when you exceed the short circuit current rating that you have a problem with smoldering and fires. Overcurrent is when you have current that's in excess of the rating of the conductor. It may result from overloading a circuit or short circuit or a ground fault. Generally happens when the solar installer doesn't take into consideration temperature correction, such as when they're basing their calculations off a 90°C temperature and they land their feeders on a disconnect switch that's only rated for 75°C, and they didn't go back and see what size of conductor they needed to land on that terminal, given that terminal is given its temperature rating at 75°C instead of 90. So they did all their calculations at 90°C and then used a box that's only rated for 75°C, and then didn't go back and say, okay, well, what's the temperature going to be at 75°C so that I apply my correction factors appropriately. That results in an undersized conductor, and that results in the conductor heating up, and it could be smoldering the jacket off of the conductor at that terminal. And so now we have an overcurrent protection device, which is a breaker or a fuse that's designed to interrupt that circuit at its maximum current rating. So we're rounding up to the next available breaker size, and then we're upsizing our conductors by 25%. So even when the breaker trips, the conductors don't smolder. So we're finding what our maximum current is, rounding up to the nearest breaker, and then also making sure that our conductors are sized so that when we do trip that breaker, we're not burning up our conductors. So whether it be a fuse or a breaker, they're both overcurrent protection devices. And you need one or the other on your solar output circuits. So your overcurrent protection device is not allowed to be higher than the ampacity of the conductor. Again, we want our breaker or fuse to blow before that conductor heats up to the point where it's burning up. You're not required to put a fuse or a breaker on the neutral wire, on that grounded conductor. So, within your disconnect switch, Well, here's one where you have your hot lead 1, hot lead 2, and then here's the neutral, and they're putting overcurrent protection in that neutral. Or you could bypass it and send it on straight through. The only time that you would land a neutral on a disconnect switch is if that disconnect switch opens all the conductors. If it opens the neutral along with the 2 hot legs at the same time. So we already have protection of conductors, overcurrent devices rated at 800 amps or less. So a 200 amp breaker, a 20 amp breaker. You do your maximum current calculation, and then you round up to the next higher standard of breaker. When you get over 800 amps, you round down. You're upsizing your conductors, and then you're staying within the rating of that conductor. And the reason for that is once you get past 800 amps, your breaker sizes get fewer and further between. Whereas when you're down at 15 amps or 20 amps or 25 amps, you're looking at, okay, my overcurrent is expected to be, my operating current is expected to be, 13 amps. So I multiply that by 25% and I get 17 amps. And so I put it on a 20 amp breaker. Rounding up the breaker size. So then we get to supplementary overcurrent protection. And this might be, fuses in a combiner box that's up on the rooftop. And so you might have some fuses up on a roof. You might have little voltage regulators up on a roof that'll turn off in the event of a ground fault. It's only the primary overcurrent protection device that's required to be accessible or readily accessible. So you can have supplementary overcurrent protection devices that do not need to be readily accessible. So just like the neutral wire is a grounded conductor, your hot lines, your power lines, leg 1, leg 2, and 3-phase, there's a leg 3. Your hot lines are called ungrounded conductors. And those are required to have overcurrent protection. They shall be located where the conductors receive their supply. At the main service panel, that's where the conductors are receiving their supply. With some exception, batteries, the overcurrent protection is installed as close to the battery terminals as possible. So usually with batteries, you're going to get kind of inline fuses. And so as you come out of the battery, and it's generally if you're not landing on a breaker within 5 feet of the battery, you're going to want to put a fuse coming out of the battery right there. So no overcurrent device shall be connected in series with any conductor that is intentionally grounded. So why is this? Well, if our neutral blows a fuse, then our ground fault detection system doesn't work anymore. And so, if our equipment ground conductor has a ground fault and blows a fuse, well, then whatever ground fault's occurring, can not drain to ground, and that electricity can stay up there as high voltage, and you can touch some exposed metal that's connected to your grounding system and electrocute yourself. So you only put overcurrent protection on your neutral if the disconnect opens all poles simultaneously and cannot open one pole individually from the other. So it's like if you want to completely isolate the power generation device from your building, you want to isolate that neutral from the building. So one example would be if you wanted to design a home with solar and a battery, but if you interconnect the solar battery to the grid, they're going to charge you more money. That interconnected neutral, you may want to open up and run your house in off-grid mode completely. And then when you need to reconnect to the grid, you may want to completely remove your solar array and battery, such as at nighttime, if your battery's completely drained, you may want to switch over to grid power and then wait for the sun to come back up to recharge your batteries. You could use the grid to recharge your batteries, but in this particular hypothetical, we're saying that the power company is going to come down hard on you if you interconnect to them directly. So there are limited circumstances where you will want to have the neutral disconnect, as well as the power leg 1 and leg 2. And you can only do that if your disconnecting breaker, such as that fuse disconnect switch we saw a few slides back, opens up the neutral and leg 1 and leg 2 at the same time. When you upsize your cables, you might upsize your conductors to get to a 1% voltage drop instead of a 3% voltage drop. You're allowed to change the size of the neutral. So here we have the accessibility requirement, where your overcurrent protection device that is not an auxiliary or additional overcurrent protection device is required to be accessible. Protection from physical damage. Mounting on open switchboards, panel boards, or controller boards that are in rooms or enclosures that are only accessible to qualified personnel is allowable. And again, that vertical position down at the bottom here is basically just saying, up is on, down is off, unless it's shown to be impracticable. So when you get over 600 volts, or it might have been 1,000. Once you get into over 600 volt systems, your overcurrent protection devices have to go up and down. If you're mounting a knife switch disconnect, it has to go up and down, even though you're under 600 volts. If you're landing on a service panel, it's impractical for you to mount that service panel sideways. So overcurrent protection is fuses or breakers. Okay, so we've already talked a lot about grounding or bonding, so I'm just going to continue to kind of click through this so that we can get further on into other sections of the code. But that supply side bonding jumper is the conductor that ensures continuity between metal parts that are required to be connected. And so you have your grounding system, which is connecting all of your metal parts together. And you have a bonding jumper that goes between them. We have an effective ground fault path, which is how ground faults are supposed to occur, running through your equipment ground conductor back to your service panel, such that a ground fault will trigger your neutral, such that your breakers will actually open up, so that your ground fault detection circuits that monitor the neutral will detect the ground fault and open up. So then you have the ground fault current path, which is how the ground fault might actually play out. Normally, non-current carrying materials enclosing electrical conductors and equipment shall be connected to earth to limit the voltage to ground on these materials. So all metal parts have to be grounded. All metal parts need to be connected to establish an effective ground fault current path. So how do we do that? Well, there's a number of ways. Welding, terminal bars inside your service panel. You have ground bars that you're all connecting together. Listed assemblies. And so when I buy my solar racking, it is listed as a ground fault path. Solder is not permitted as a ground fault path. But what does that mean? Well, I might have some metal netting, and I might say, okay, well, I'm not using a listed metal netting to put around the perimeter of my solar array to protect my array from debris or rodents getting underneath the array, but I'm using a metal netting, and so I need to ground it somehow. And so what I'm going to do is I'm going to land a ground lug on my solar panel, and then I'm going to take a ground wire over to my netting. I'm just going to solder the ground wire to the netting. That is not permitted. Solder is not permitted to be a ground fault path. They really want you to use a listed assembly or some kind of connection that is like a ground lug or a grounding screw that is actually intended to be your ground fault path, with the exception of welding. You know, they're not trying to make you go buy equipment. They're just saying, you know, a weld is a much more secure attachment than soldering. You know, so when you go to install the ground rod on the side of the building, you have a little fastener that you run your grounding into, and it's just a clamp that secures your ground cable to your ground rod. You know, I find myself these days in Mississippi installing two ground rods, like a secondary ground rod right next to the first, and running my ground wire to both of them. So I don't really trust that connection to stay forever. And in Mississippi, we have some weird soil where it's not very conductive. And so I like having that extra piece of copper into the ground. Another thing that's weird about Mississippi is you can drive a ground rod 8 feet into the ground without any equipment. It's a weird technique, but you basically take your ground rod, which is 8 feet long, and you poke a little hole in the ground and you shove your ground rod into it, and then you take it back out and you pour water down the hole, and you can just kind of keep driving that ground rod deeper and deeper and deeper by adding water into that hole, and just goes, it's like mud, and just sucks it right in. So if you're using a ground clamp, if it's exposed to physical damage, it should be enclosed in wood, metal, or equivalent protective covering. You shouldn't just have your ground rod, kind of sticking out of the ground here with that ground clamp there and the metal going and attaching to it. If you're sticking a little bit out of the ground with your ground rod, you need to sheathe that ground rod so that no one comes by and kicks it, disconnects your building from ground. Here's an example of a little grounding washer that grounds the metal module frame to your racking system. Your module frame has an anodized coating, and these little teeth or dimples inside the ground washer cut into that coating as you're screwing it down, and kind of bites in. If you remove it, you'll notice little scratch marks on the panel where the ground washer has scratched through the anodized coating. Those alternating current systems should be grounded systems. And remember, that's the neutral connecting to ground. It says DC systems shall be permitted to be grounded. Does that mean you don't need to ground a DC system? Well, the answer is no. You still need to have an effective ground fault path for all your metal parts, your metal module frames, your metal racking, your metal boxes. They all need to be connected to that ground fault system. It's more that on a DC system, you have your positive and negative, but on the DC side, there's no neutral. Remember, it's that neutral that you're connecting to ground. So, some older architecture would connect the negative side to ground and only fuse the positive side. What's more common these days is to have a floating system where neither the positive or negative on the DC side is connected to ground, at which point you fuse both the positive and the negative. So the grounding electrode conductor connection shall be accessible from the load end of the service drop to the terminal where the neutral is connected at the service disconnect. It can be made at any accessible point. And so what that means is anywhere between, say, your meter base and your service panel, the load end of your service part, to the terminal which the neutral is connected at the service disconnect. The service drop is up here where your transformer is. And so you may need to see if your neutral is already kind of bonded to ground out at your meter base rather than at your service panel. You may be carrying it through to the outside and connecting it to ground, elsewhere. And that's usually what happens. Usually you're bonding neutral to ground inside your service panel, and then the neutral is being carried out to, the service disconnect where your ground rod will then emerge. The neutral shall not be connected to your equipment ground conductor or reconnected to ground on the load side of the service disconnect, except in certain cases. That's like if your ground rod is coming out of your service panel. So the main bonding jumper is the term for that cable that connects in your service panel, the neutral in your service panel to the grounding bar in your service panel. And that main bonding jumper needs to be unspliced. It's not a very long bar or cable. Sometimes it's integrated directly into the service panel. I recently installed a service panel where it looked like on the right side there was a neutral bar, and on the left side there was a ground bar, and they were bonded together through the back of the panel through a metal plate. Well, if we use that panel as a load side distribution panel, what we would have instead is two neutral bars, and we would need a separate ground bar that was not connected to the neutral, because that would not be the appropriate location. A sub panel on the load side is not the appropriate location for your main bonding jumper. Your main bonding jumper is made in your service disconnect enclosure, that main service panel. So the neutral should be routed through with the ungrounded conductors to each disconnecting means. This says for AC systems. Not all solar inverters require neutrals. Where you need a neutral with a solar inverter is if you're landing on a sub panel. Let's say you have a 240 volt inverter, but you also want to put some 120 volt circuits up at whatever panel you're landing, sub panel you're landing your inverter on. That's when you would need a neutral on the DC side. For AC side, it's a requirement. So when you start getting into larger and larger cables, and we'll talk about this in section 300, and we're going to take a break soon. I'm trying to get out of this section 250. But when you get into larger and larger cables, you may want to start breaking them up into parallel runs. And the point is, when you're going into parallel runs, you need to run your neutral and your equipment ground conductors in both parallel runs. You know, as we'll see when we get into section 300, your parallel runs, your parallel raceways need to have similar characteristics. They need to have the same number of conductors and the same and shit, you know, and have their own neutral and ground in them. You're not going to run your hot leg in one conductor, your hot leg in another conductor, and in another raceway, and your neutral in another raceway. You know, they need to have, the raceways need to share equivalent characteristics. And then your grounding electrode conductor is the last kind of the last run where you've connected your neutral to ground. You still need to connect your ground to the actual ground. And your grounding electrode conductor is the last stop. We talked about that yesterday, where it's going to be a much larger cable than your neutrals that come back to your service panel, or your equipment ground conductors that come back to your service panel. You know, the grounding electrode conductor is equivalent to your sewage pipe that drains out to the city sewer system. It's your ground that drains out to the earth grounds. So the grounding electrode conductor is the final ground cable that goes between your electric service and the grounding electrode. That's not to be confused with the grounded conductor, which is your neutral wire is a grounded conductor. Um, and we have some discussion of what a separately derived system is. A separately derived system does not share a neutral. So a separately derived system may have two separate bonding jumpers, but it would require a complete disconnect between one bonding jumper or the other if you're trying to power the same load with two separately derived systems, such as a backup generator and and the grid power. If you want them to be separately derived, then you'd have to have a disconnecting neutral. The building grounding system, though, does not need to be separate. And you can still have one grounding electrode. You can have a separate grounding electrode as your main general grounding electrode conductor if you want. You're allowed to have, you know, a grounding electrode by your service panel and a grounding electrode by your generator. And if you're completely disconnecting from the grid, you can say, well, when I'm in my generator mode and my switch is opened up and I'm separately derived, this is my grounding electrode conductor and grounding electrode, and disconnect the one over at the service side of the system with the main. So then we start getting into rules of what is allowed to be a grounding electrode conductor. It starts out to say it has to be 3/0 copper or a water pipe or the metal frame of a building. But then there's various exceptions that will kind of whittle the size of that grounding electrode conductor down. You're picking out the size of your grounding electrode conductor based on, basically the amperage of your electric service. The minimum requirement's going to increase as your service goes up in size. And this is just kind of some redundant stuff. The key takeaway is to not connect your neutral to ground until you get to your service equipment. So when you're supplying multiple buildings with the same power source, so let's say you have a garage in a home, or a home in a garage apartment, and the garage apartment's on a sub panel. You're routing your neutral from your main panel back to that sub panel, but at that sub panel, even though you may have a grounding electrode at that sub panel, like a ground rod, and your equipment ground conductor being connected to ground at that panel, at that sub panel, you don't have a main bonding jumper. You're not connecting neutral to ground at that sub panel. That neutral to ground connection should only be made in at the service equipment of the building, of the main supply. There's special rules for portable generators. Your permanently installed generator uh, should have an effective ground fault path. It says if the generator is not separately derived and the overcurrent protection is not integrated into the generator assembly, a supply side bonding jumper should be installed from the generator equipment ground and the equipment ground conductor of the disconnecting means. All right, so now we're into what constitutes a grounding electrode. The most common one is a ground rod. But using a water pipe that's underneath the building. This is kind of interesting. It says metal in-ground support structures that are driven into the ground 10 feet or more. And so if you're building, say, a solar ground mount and you're driving metal piles into the ground, you could think, well, do I need a grounding electrode conductor? Because aren't grounding electrode? Because aren't my piles serving as the ground? Not necessarily. Those piles generally are not going down 10 feet. It's common that they, even on a utility scale fixed single row ground mount where all the panels are just on one row of piles as opposed to two rows of piles, those piles are typically only going down 8 feet. And often they're galvanized. So they're usually, the racking manufacturer will tell you, no, you can't use them even if they're going down 10 feet or more. Now, when you're building a concrete foundation, you have a lot of metal in that concrete. Concrete's kind of funny in that it doesn't have a lot of resistance, but it can have a lot of resistance. So when concrete is wet, it can have resistance. And so in your batteries, your battery boxes, when you get into the later battery sections, you can't just set your batteries right down on the concrete. You have to have an insulating pad between your batteries and the concrete, because if that concrete gets wet, electricity can conduct through the batteries into your concrete. At the same time, even though you have a lot of metal in that concrete, that metal in the concrete, that rebar, can only be used as your grounding electrode conductor if you have 20 feet or more. So that's a quiz question: is when can you tie your grounding electrode conductor into the rebar of your concrete and call it the grounding electrode? As you have to have 20 feet or more of rebar for that. That seems to be a common exam question. So you can have a ground ring where you're taking copper wire and you're just running it around the perimeter of the building as your grounding electrode. That might be if you're in soil type that if you go down 3 feet and you have a big rock shelf, you can't drive an 8-foot ground rod into the ground. You might go with a ground ring instead. And so when you go with the ground ring, they're saying the minimum size of that ground ring has to be number 2 AWG, which is pretty thick. Or you could have a 8-foot copper ground rod driven into the soil, which is, I feel like that's the most common one. And so particularly on residential new construction and off-grid new construction, you're going to have to drive a ground rod into that building. Or if you're doing a battery box in a battery room, that's a separate structure from the building, you'll want to drive a ground rod into that building. And even though you're carrying the neutral back into the main building with the main with its own ground rod and grounding electrode. Gas piping, aluminum wires are not allowed to be the grounding electrode. Grounding electrode system installation, supplemental electrode required. A single ground rod, pipe, or plate electrode. So when you're using a ground rod or a water pipe or a plate, you need to supplement it with an additional electrode such as another ground rod. Usually you don't get into that because even though you have one ground rod out at your house, you're carrying your ground back to the utility transformer at the pole where they're putting in their own ground rod. But if you're designing an off-grid house, just drive in 2 ground rods instead of 1. When you're using a ground rod, the grounding electrode conductor is not required to be larger than number 6. And as we'll see in section 300, number 6 is allowed to be supported by itself bare without any insulation or without being in like a raceway. And so it's very common to see number 6 copper being used as your grounding electrode conductor. I think this is a typo. It should be rod and pipe electrodes. The hardest part about driving a ground rod is making sure you got 8 feet of that ground rod in contact with soil. And there's actually procedure in code that says if you're driving your ground rod and you encounter rock, the next step is to drive the ground rod in at an angle instead of straight down. And if that doesn't work, you need to throw your ground rod in a trench that's at least 30 inches deep, similar to a ground ring that needs to be 30 inches deep. And it says the upper end of the grounding electrode shall be flush or below ground unless protected from physical damage. So if you have a 10-foot ground rod, you can stick it out of the ground, but you'd still need to house it in some Schedule 80 PVC or something so someone doesn't come around and kick it. The same electrode shall be used to ground the grounding conductor enclosures, AC systems of all the equipment in or on that building. So we have number 6 copper or larger that's not exposed to physical damage. So, if it's not running along a driveway where cars could hit the ground rod and jerk the copper out of the grounding electrode clamp, is allowed to run along the surface of the building without metal covering or protection. And so often you'll look and see, solar conduit coming down the rooftop, and you might see bare number 6 outside of that conduit hugging it and then splitting off and going into the ground, that being your grounding electrode conductor. If your grounding electrode conductor is smaller than number 6, then it has to go inside conduit. Grounding electrode conductors need to be a continuous length without a splice or joint, which means when you're connecting the ground bar on your service panel down to your ground rod, only at that location does it need to be continuous. So if I'm up on the rooftop and I'm connecting all of my modules together with module clips, and then I run my equipment ground conductor up to the roof and landed on that equipment ground conductor can be spliced inside a box, then come out the other side of the box and go into another box and come out the other side of the box. It's not the equipment ground conductor that needs to be continuous. It's the final leg of your grounding system, the grounding electrode conductor that needs to be continuous. Well, there are ways to splice the grounding electrode conductor if you have to. You know, the most popular one is getting a very large crimping tool and the little copper clamp that wraps around two pieces of bare copper and gets pressed together. It's called an irreversible crimp. And you got to put a lot of muscle into it and make sure you tug it to make sure you've made that irreversible crimp so it doesn't slide out. Or section of bus bars bolted together, welded connections. So raceways and enclosures for the grounding electrode conductor need to be continuous from the point of attachment to the grounding electrode. That's what the GE stands for, is the grounding electrodes, the actual ground rod or ground plate. And then bonded at each end of the raceway or enclosure to the electrode or the grounding electrode conductor to create an electrically parallel path. So what does that mean? How, if you're running conduit from your service panel to ground, you know, you can ground your conduit here. We're going to talk about that in a minute. But at this point, your grounding electrode needs to come out of the conduit and attach to your grounding electrode. And so what you would need is a grounding bushing here so that you can run that grounding electrode conductor through that grounding bushing and then into your grounding electrode. And so that's why like number 6 is much more common to see than number 8, is because you don't need this conduit to protect it. The grounding electrode conductor shall be sized for the largest grounding electrode conductor required amongst all the electrodes connected to it. And so the only thing I have to say about that is for very large commercial arrays where you're only using a single inverter, the amperage, if the amperage of the DC array is larger than the amperage of the AC service. It's very rare when this happens, but it would happen if, say, you have a large warehouse. And so the warehouse, all things considered, doesn't have as high of an electric load as, say, like an office building of equivalent square footage. And you cover the whole roof in solar, you might have a 800 amp solar array and a 400 amp electric service. And you might determine that the grounding electrode conductor on the DC side is larger than the grounding electrode conductor on the AC side. And you may not have a ground rod. You may have a ground ring or, you know, something else that gets you out of being able to elect to the down to the number 6 and instead having to use the full-sized grounding electrode conductor. So it's a rare circumstance, but if you find yourself doing a large commercial array on one central inverter, you know, check the amperage of the DC side to see if you need to upsize your grounding electrode conductor. So if you're using, again, if you're using a ground rod or pipe or plate, it's not required to be larger than number 6. But for instance, if you're using the rebar in your concrete foundation as your grounding electrode conductor, that's when you would need something larger than that. In this case, it's number 4. Again, because that concrete is less conductive than just regular soil. And I just usually always use ground rods. The frame of a building can be used to connect uh, a conductor. You can run your grounding electrode conductor onto your building frame, or your equipment ground conductor onto your building frame, and your grounding electrode conductor out of your building frame under special circumstances. And we're using special fasteners. On residential electric service, that for small facilities, 100 amp service, a number 8 is the minimum size of the grounding electrode conductor. If you're going into residential, number 4 is the smallest, unless you're using a ground rod, at which point you can use number 6. I guess the word of caution is your local jurisdictions may have requirements above and beyond National Electric Code. So out in Mississippi, where I live and work, although right now I'm in West Virginia, but out in Mississippi, our soil is not particularly conductive. And so some of the electrical co-ops, require you on 400 amp service to use number 4 as your grounding electrode conductor, even when you're using bare copper and connecting to a ground rod. They want to ensure that you have that. Really, the connection to ground is coming from the ground rod itself. So to increase the to decrease the resistivity between the ground rod and ground, the best way to do it is to require 2 ground rods instead of 1, and just put them right next to each other and attach to both. So metal enclosures and raceways shall be grounded. Again, I think that's a strong argument to use plastic enclosures and raceways on a roof for your solar conduits, because it can be it can be hard to find the right components where you can get the right cable glands to just come out of the conduit that have a grounding bushing integrated into it. When you're landing your conduit, metal conduit, on a metal box, you're grounding your conduit to your box. And we're going to talk about that in a minute. But when you're just looking to kind of support your cables as you're running across a commercial roof, you're not always having a metal box to land on. So by requiring it to be in metal conduit, then you're also requiring the purchase of metal boxes, which look ugly and clunky and are not waterproof or prone to leaks. There's a lot of water on flat rooftops. And so I think that kind of begs for plastic raceways up on rooftops. There are exceptions. It says short sections of metal enclosures or raceways used to provide support or protection of cable from physical damage shall not be required to be connected to the equipment ground conductor. So what might that be? Well, let's say you're wanting to transition between the attic and the roof, and so you want to stub up a 6-inch piece of rigid metal conduit through the attic into your roof and come out in a cable gland. You know, that's not necessarily required to be grounded. Then again, if it's more than about 6 inches, then an inspector might say, well, that's not really a short section, that's a raceway. You know, even if you have metal going into a plastic box and metal coming out the other side, you need to have a plan for connecting the ground from one side to the other, whether it's having a grounding bushing on both sides and running a bare number 6 between the two, or having a ground rod, you know, on the inside the box, a ground bar, sorry, inside the box that the metal can terminate onto. And this, I think, is another kind of lesser known grounding issue. And you get these metal boxes. They're electric service panels. They're the inverter frame. They're you know, just metal boxes to terminate your conduit on. They have these knockout rings on them, you know, for a 3/4 inch conduit, for 1-inch conduit, and often they're various sizes, and so you have a small hole and a large hole, and so when you're doing your design, you're like, well, which is the best to use? Do I go in, if I have 3/4 inch conduit, do I go into the 3/4 inch hole, or do I knock out the 3/4 inch hole that's inside the 1-inch hole? Or you might have a choice to say, well, I only need 3/4 inch conduit, but the inverter has a 1.5-inch knockout. And so should I upsize my conduit to 1.5 inches, or should I stay down at, you know, the 3/4 inch and use a reducing washer? Code has something to say on that. You know, let's say you're banging away on this knockout, and you use the smaller side. You know, or let's say you're creating your own hole. There's a triangular bit for drilling your own hole into a metal box, or you might have a hole saw. And let's say your crew is getting a little ahead of themselves, and they actually drill a hole that's too large for your fitting. Uh-oh. The hole's too large. The conduit doesn't land in the hole as it should. There's no way to get our lock nut down into it because the hole's bigger than the lock nut. Or you can get a reducing washer to get you down to the size of the hole you need. But whether you're using the interior hole of like a ringed knockout that gives you multiple sizes, or you drilled your hole too large and now you're using a reducing washer, these are considered impaired connections. You know, this reducing washer is not connected to that wall of the metal box like, you know, any individual section of this metal is. You know, this if you use the inner hole rather than the outer hole, you're still going to have these little dimples to deal with. and that dimple is a little kink in the metal instead of a full thickness of that metal wall. So that's considered an impaired connection. So while standard lock nuts and connectors and compression couplings, if I'm running metal conduit into a metal box and using a metal connector, that is considered grounded. If I land on an impaired connection, it is not considered grounded. And so at that point, you need to use a grounding bushing. That has a little, little terminal lug for your copper ground wire that you would then need to go and land on a ground bar inside that box or inside that panel. So, if you're going with EMT to EMT using threaded couplings or other couplings and fittings that are listed as a ground path, that's considered to be bonded. If I'm going into the top of a metal box with rigid conduit and screwing it into a Myers hub, that's considered to be bonded. Be aware that when you're bonding to your metal box, you need to make sure you're going through the paint. So generally, your metal boxes will have a ground screw that will go through the back of the box to make sure that you're grounded to that box. And kind of see some minimum sizes of grounding electrode conductors, which we've seen before. Oh, well, no. So now we're looking at the I think this is the size of the EGC, equipment ground conductor. So normally with solar, when you're doing a solar array to power a building, your cables are coming out of the inverter are number 8, number 10. Sometimes a little bit larger, maybe from if it's a particularly large inverter, maybe number 6 or number 4. Whereas your service entrance conductors are 2-aught or 3-aught. So normally your equipment ground conductor is going to be number 8. And so I'm always going to run like a number 8 up to the rooftop and land it on my racking. And then that number 8 is going to go down to my service panel and land on my ground bar. And then with my service panel being a larger service entrance cables of 2-aught or 3-aught, then I would need a larger grounding electrode conductor, except that I'm using a ground rod, so I can elect this to be number 6. So the general rule of thumb for, say, residential solar is to run number 8 up to your racking for your DC grounding electrode conductor. And then since your AC grounding electrode conductor is going to be number 6, you don't need to worry about the DC being smaller than the AC or larger than the AC. You just run that number 8 down and you bond it to the AC grounding grounding equipment ground conductor system, and run that number 8 down to your service panel, land it on your ground bar, and then go number 6 bare out to your ground rod. Exposed metal parts of equipment with energized parts should be connected to equipment ground conductor. We're subject to contact by people. I'm just going to keep moving along. I'm trying to get out of this section. EMT is allowed to be an equipment ground conductor. Although it's, so your EMT is going to be grounding your metal boxes from one metal box to the other to the next. So if you're not using bare copper wire for your ground conductor, like that number 8 up to the rooftop to land on your racking, it needs to be green jacketed. It can't be taped green to say this is my ground wire. If you're using a sheathed cable, not a bare cable, but a sheathed cable, it has to be in green until you get up to number 4 or larger, at which point you can use green tape to identify it. We're just going to move along in the interest of time. When ungrounded conductors are increased in size, the equipment ground conductor shall also be increased in size. On commercial arrays, if you're upsizing your equipment ground conductors because you want to reduce, you're upsizing your power conductors because you're trying to reduce voltage drop, you'll need to go back and refer to the chart to say what's the size of my conductor and what's the minimum size of my equipment ground conductor. So when you run your circuits in parallel, you need to run your equipment ground conductor in parallel as well. And so here we get to the table that shows the minimum size of your equipment ground conductors for various circuits. And so your solar circuit, it's larger than 20 amps. Generally it's 60 amps for your typical solar inverters, although if you were installing a giant solar inverter to power your whole house, and your whole house was a 200 amp service, then you would need a larger equipment ground conductor. I usually, just for solar, stick to number 8. The reason being, it's a little murky on if you need a DC grounding electrode conductor, or if the components, all the metal frames and racking and boxing, simply need to be attached to your equipment ground. And so I just always run number 8 up to the rooftop and conduit and land number 8 on my racking and be done with it. And keep going. So while the metal frame of your building may connect grounding electrode conductors together, it should not be used as your equipment ground conductor. So your equipment ground conductors need to all go back to, say, a ground bar, where then they'll connect to the grounding electrode conductor, which then may go and attach to the metal frame of your building as your grounding electrode, but not before that point. Again, we're saying don't bond your neutral to ground on the load side. So the equipment ground conductor associated with circuits spliced or terminated in a box must be connected to the box. So generally, let's say you have a metal box where you're performing splices in. You're going to run your equipment ground conductor into a ground bar on that box, and then run your equipment ground conductor out of that same ground bar through the other side of the conduit. So one way to say, okay, well, I don't want to deal with grounding my box. I'm going to use a plastic box instead of a metal box. Well, you still have to carry that ground through. And so now you might have a metal conduit going into a plastic box and a metal conduit going into a plastic box. And instead of having your metal fitting saying, oh, we serve as an equipment ground path, and so we're connecting our ground on one side of the box, we're connecting the box to the ground, and then we're taking it out from the other side of the box with our conduit to the box. Now we have to use grounding bushings and connect the metal conduit on one side of the box to the metal conduit on the other side of the box. And then you still may need a ground bar on that plastic box if you're doing splices inside of that box. So a grounding connection for DC side, it's similar to AC side. The size of the direct current grounding electrode conductor for a DC system shall not be smaller than number 8 or larger than 3/0. Not required to be larger than number 6 when using a ground rod, pipe, or plate. It's pretty much the same requirements as the AC side. Now, if you're using a floating system, you're not connecting that negative to ground. You don't have a grounding electrode conductor. And so that's where some installers say, no, on DC floating systems, you just have an equipment ground conductor. There is no grounding electrode conductor. Which is why I always just use number 8 on my inverters that are 100 amps or less, even though you might be able to get away with less. Now, as far as ground fault protection goes, that's pretty much built into the inverter sensing circuits already. The inverters are listed for ground fault detection and arc fault protection. So an unspliced bonding jumper shall be used to connect the equipment ground conductor to the grounded conductor at the source of the first system. Disconnecting means when the system is grounded. In the interest of time, we're just going to keep moving forward. So now we're in section 300. Parallel conductors. You're allowed to run parallel conductors, but only in a specific circumstance. All the conductors of the same circuit have to be contained in the same raceway, except when you're doing parallel installations. When you're doing parallel installations, you still have to have the same characteristics in each paralleled raceway. It says, conductors of AC and DC circuits are allowed to be in the same raceway, but your solar conductors have to be separate from your non-solar conductors. So you can't run AC load circuits in the same raceway as your solar conductor circuits, with the exception of like load control management devices and stuff stuff that's still related to the energy system itself, not an auxiliary power outlet or an external lighting circuit to give the solar array some light. Those need to be run in separate raceways. But you can combine your AC and your DC. If you're running it under your roof decking, it needs to have 1.5 inches of clearance. If you have corrugated metal roof and you think you're kind of smart for running conduit in that gap, it should not be concealed inside the metal corrugated roof. You need that clearance there so no one drives a roofing nail through the rooftop and hits your conduit and nicks your power cable. There are depth requirements when you're running your power cables under in a trench. It gets Not sure really what that. I think I must have left something out of this one, but going under roads and under driveways, you need generally your local jurisdiction is going to tell you how deep you need to go. You put a conduit under the underground, it's considered a wet location. Now, I'm a big fan of direct burial cable. And the reason why I like direct burial cable is generally you're not going to have a lot of traffic on between a solar ground mount and a home. Um, even a driveway is not going to be used all that much. If it's a heavy use driveway, then maybe. But the question is, well, when do you go with? So what you do with direct burial conduit is you dig your trench, and then as you're digging your trench, you're just throwing the cable into that trench, and then you backfill it and put down your little warning line, and that's it. Otherwise, you dig your trench, and then you're having to build your conduit as you go along, and then you have to put the conduit in the trench, and then you have to come back and pull your cable through the conduit, and it just takes forever and a half. And again, that conduit is not really going to be multiple use. And furthermore, the conduit's going to accumulate water inside of it. And I don't like the idea of the solar cables just sitting in water. I'd rather that water drain or get into the earth. And so what happens when you're digging your trench is as you're getting, emerging from grade, getting out of your trench, only that one section is conduit. And so you may see a cable going into the ground and it's in conduit. That doesn't mean that conduit is extending the length of the trench. And utilities do direct burial all the time, outside of conduit. You still need to, especially in colder climates, give yourself, some slack if you're doing direct burial so that your frost heaving doesn't rip your cable apart. So if you're doing direct burial and you're coming right up underneath where your solar array is going to be, you need to give yourself an S loop. I'm just going to kind of keep moving along a little bit. Non-metallic conduit should be listed for exposure to sunlight. So like, electricians have their own PVC for plastic conduit. It's gray colored to give it some sunlight resistance. So here it's saying not just when emerging out of the ground, but when emerging from different temperature differentials, it needs to be sealed. We already talked about that. No supporting your cables or raceways by your drop ceilings. Now here's another one: mechanical continuity. Raceways shall be continuous. Well, okay, but what if I have a solar array and then I have another solar array, and I just have a little short section where I need to jump from one array to the other, am I allowed to just have some freestanding plastic conduit here to run my cables through so that they're not, exposed, so that they're protected? And yeah, short sections used to provide support or protection of cable assemblies are allowed to be non-continuous. That doesn't mean they're not, we saw in another one where they don't even have to be grounded, but then it becomes kind of a issue of what is the definition of a short section. I would consider to be a short section to be something that's less than 3 feet. So you actually can do splices inside of, raceways. So can you splice inside of EMT conduit? Well, if you figured out how to, you could. Provided that the splices are accessible. So inside EMT conduit, it would not be accessible. But if you had a fitting that had a removable lid that isn't necessarily a box, you can put a splice inside of that, provided that it doesn't fill up more than 75% of the area at that point. So where that comes into play is you might have a big meter base, and you have your utility conductors coming out of your meter base, and you might say, okay, well, can I tap my solar array right inside my meter base? You'd usually use something like these ILSCO tap connectors. Like this, where one conductor's coming in from the meter, and then another conductor's coming in from your solar array, and then another conductor's going out towards your service panel. And so you essentially, cut this cable here, and now you have 1, 2, 3 cables. So you get a 3-hole tap connector, 1, 2, 3. So can you just open up your meter base, provided your utility gives you the thumbs up, and put these tap connectors right inside the meter base to tap on? The answer is, well, yes, but they can't fill up more than 75% of the area. And that's why it might surprise you that, like, when you're looking at junction boxes, why they get just so dang big is because, if you're doing a lot of splicing inside that junction box, you can't take up more than 75% of the cross-sectional area at any point across that box. This is just to say, you need to leave 6 inches of wiring in your lighting boxes. It's not really a solar thing. I'm just going to keep going. So some of this stuff I'm going to keep skipping over so we can get into some key takeaways for solar and batteries. So I was kind of surprised to learn when I was doing calculations for Raceway and conductor fill that you're typically sizing your conductors to be no more then, and it depends on if you have two conductors, you get a little bit more fill. If you have three conductors, you actually get a little bit less fill than two. And the reason is once you start adding more conductors, they start twisting and binding. And so it actually, you need more space, empty space in your conduit for more conductors. But the point is, you need enough empty space in your conduit for your conductor to be able to pull through and also dissipate heat. And so typically your conductor fill is like 30% to 40%, depending on how many conductors you have inside your Raceway. So as an engineer, if I'm thinking, oh, the conduit is 60% empty, that's a lot of empty space. You could squeeze another cable in there. But you actually need that empty space in order to pull the cable through the conduit and fitting without scraping up the cable jackets. Again, the exception is short sections of raceways, which I would in this case consider to be not just for structural support, but like connecting from one box to the next box. I would, not to feed under some stairs and have them be kept up off the roof, but, if I'm going from one box to the other, I would consider a short section to be 6 inches or less. You can put a few more in. I'm just going to keep moving forward in the interest of time. So you can actually you go through a fire rated wall. You need to put fire stop sealant into it to maintain that fire rating. When you're selecting your cable, there's all these different kinds of cable. And the biggest thing is if you're in a wet rated environment, you need that W. And if you want some sunlight resistance, you need that -2. And so generally with solar cable, we're going with like THWN2. Whereas if you're going with typical wiring inside your house, you might go with THHN, which is a substantially thinner cable jacket. If you want to do parallel runs to downsize your wire and make your parallel runs easier, you can only do parallel runs of where the cable size itself of the parallel run, not the starting cable size that you're cutting in half for your parallel runs, but the final parallel run. Each side of that parallel run needs to be 1/0 or larger. The temperature rating of the conductor should be selected to not exceed the lowest temperature rating of any connector, termination, conductor, or device. Conductors, and then it says something kind of opposite. Conductors with temperature ratings higher than the specified termination shall be permitted for ampacity adjustment, correction, or both. The takeaway of this is you need to check your, as we said yesterday, the temperature rating of your terminals, and make sure that that is make sure that when you're doing your temperature adjustment for that home run conductor, you also redo your calculation for the terminal itself, and making sure that the temperature on that terminal point is not going to be of a higher temperature than what the terminal is rated for. And so we kind of talked about this, these temperature ratings yesterday. But for example, on a rooftop in Phoenix, Arizona, it is quite possible for the temperature to get above 75°C ambient. And so the best practice is to make sure your rooftop boxes have terminal temperature ratings of 90°C. We talked about this chart yesterday, so I'm just going to keep going. Actually, in the interest of time, um, you need to do ampacity adjustments when your raceways are larger than 24 inches. So there's actually a change in National Electric Code. It used to be based off how far the conductor was off the rooftop surface. You would derate it by a certain amount. So 0 to 1 inches, and then it was like 1 to 3 inches, and then greater than 3 inches. Pretty much that changed, that said if the cables are within an inch of the roof, or less than 7/8 of the roof, you have to add 60 degrees to the outdoor temperature. Which is a lot. Basically what that says is keep your solar cables, an inch or more up off of the rooftop. Then there's an additional derate factor for how many conductors are inside that conduit, because these conductors generate heat. And there's certain cables that are rated for higher temperature ratings. So I'm just going to kind of skip forward to the solar section and battery section. And, if you have questions about other stuff in the content that we're skipping over, I'm a big fan of metal clad cable. Except in a battery room, that metal clad cable would need to be given some corrosive treatment, like paint, or using a seal tight conduit that has a plastic jacket with metal on the inside. Some jurisdictions require something more robust than metal clad cable, like in New York City. Maybe in apartment buildings and skyscrapers, they may require even something more robust than EMT conduit. Sometimes they require IMC conduit, which is a little bit thicker. So I'm gonna just kind of blaze through these slides and call out anything that I think is the most important. Um, so then we get to there's actually section 480 for storage batteries. And this is one difference between US code and international building code. It says batteries have to be listed, and remember that means listed for purpose. And so in the US, it is technically a code violation to take a used electric vehicle battery, such as if a Tesla's in a wreck and they scrap the batteries, and you say, okay, I'm going to buy those batteries and use them on my house. They're not listed for purpose. In international building code, you're allowed to do that. But it says this requirement shall not apply to lead acid batteries. Reason being is lead acid is generally lower voltage and less volatile than lithium ion. And so what that means is you can use a refurbished forklift battery for an off-grid home, but you can't use a refurbished electric vehicle battery for an off-grid home at this time in the eyes of National Electric Code. But that's not a universal code. In other countries, you can. Disconnecting means within sight of the battery. Unsealed batteries need to be in vented rooms. And the definition of a vented room varies and is a little bit different between NEC and International Building Code. What you will typically do is put a hood over your unsealed batteries and vent them directly to the outside. And the gas is lightweight in a battery room, so it'll rise up into the hood with a small fan for continuous venting. Unsealed batteries corrode, and so you need to paint your metal inside your battery room. Just remember that just because the metal is painted doesn't mean that it's considered insulating. So your batteries also have to be on an insulated pad. An air-conditioned space is considered to be a ventilated space. Live parts guarded against accidental contact. Your batteries have to have a 1-inch clearance away from the wall. The battery stands do not. If you have live terminals that are exposed in your batteries, then they need to be guarded or at least in a locked room. I had a client that was kind of upset because he's like, oh, I can just touch my battery terminals and electrocute myself. It's like, well, we built a shed outside your house that's locked, and all it does is contain the batteries. So don't go in there if you don't know what you're doing, and you need to put a lock on that shed so that people don't go in there who don't know what they're doing. There are ventilation requirements for the room for batteries. What I want to do, because again we're creeping up on the end of time, is to highlight a couple of major things to know about what's going on in solar. When you're calculating the module ampacity, you take the current and you multiply by 25%. And then you adjust for like temperature correction. That's if the array is not governed by voltage regulators or controllers that can throttle the power output, like microinverters or solar edge optimizers. At that point, it is just a 25% upsizing. Arc fault protection is now built into most inverters, so the inverters themselves will detect arc fault. So now we get into a requirement called rapid shutdown, and this has been changing. It used to be that within 6 feet of the array, if the utility needs to shut off power to the building, all energized conductors within 6 feet of the array need to power down. It's since been curtailed to within 1 foot of the array. But the most controversial part is whether or not, for most standard arrays, this PV array with no exposed wiring or metal parts is very rare. There are fiberglass racking systems and frameless solar modules that you can find that don't have any exposed metal, but it's very rare. So now you got two options during a power outage. The first is to put, if here's your solar array, inside the array perimeter, you put little boxes behind each one and control the power output so that the power is killed at each box. Or you have an array that is, and this is the controversial part, listed or field labeled to be a rapid shutdown array, which is an array that de-energizes all the power within 1 foot of the array. And so a lot of installers are interpreting this to say, okay, well, now you have to have these module level panel electronics behind every panel to be compliant with NEC 2017. I look at it differently. I look at it as you need to have a sticker that says the solar array is rated for rapid shutdown, meaning that within 1 foot of any perimeter of the array, the conductors outside of that 1 foot de-energize. And the big difference would be is that would allow you to mount your inverter, say, in the attic, within 1 foot of the roof deck. And so if your inverter is located underneath the array or up on the rooftop right next to the array, but still within that 1 foot perimeter, it still is compliant as a rapid shutdown array. Now there's no arrays that are listed as a rapid shutdown array, but it does say or field labeled, and it's very common to field label an array as a rapid shutdown array. So I don't actually think that NEC 2017 is mandating module level panel electronics. You know, when you're wiring your solar array, there's two kinds of wires you can use up on the roof outside of conduit. PV wire is what it's literally called, and that's the most common. USE2 is also acceptable. It's a little bit cheaper. The big difference is PV wire is rated for higher voltage. When you go inside the building with DC, it has to be in a metal raceway. That's the big difference between, I think it's DC discrimination. I don't think there's a good solid justification on why an AC feeder circuit inside a building does not need to be in metal conduit, but a DC feeder circuit does. It's not a grounding issue, it's a physical protection issue. But even so, DC inside a building needs to be in metal, which is why I'll usually run metal-clad cable through the attic. It just makes the install much easier and quick, and it gives you that nice internal conduit run. You are allowed to put boxes behind the panels. And so what I'll try and do is have my solar array up on the rooftop, and then I'll put a transition box underneath the panel at the end, and then I'll stub up my MC cable into that box, and then run my loose MC cable out of my soffit, and then land a box out of my soffit where my house is. So this is the attic now. And then land an EMT conduit onto my inverter. And the reason why I do that is up on the rooftop, you don't have any exposed wiring or conduit because we're going into the attic right then and there. It makes the array look like it's magically hovering above the rooftop and gives you a really good, clean aesthetic, which I think is critical to maintaining the long-term value of the system. And we're over time, so we're going to be wrapping things up real quick. Then we get into energy storage systems. And I think the most important part of energy storage systems, we kind of talked about the 20% rule yesterday. And I do put these recordings on my YouTube channel. So again, I'm going to put my email address in the chat box in case some of y'all need to jump out and chat. They will send you the quiz link either right after this program or within an hour. So if you have to leave now, you'll just check your email for the quiz. So Article 706 governing energy storage systems only applies to battery banks that are over 60 volts. So most lead acid batteries are going to be at 48 volts or less. So this is really a lithium ion battery section. But even so, it's worth paying attention to. The disconnects from the batteries should be within 5 feet of the battery equipment. And even with the lead acid battery, I think that's good standard practice. If you pass through a wall or a partition, you need another disconnect switch. And then we see stuff like we did otherwise, like a minimum clearance of 1 inch between the wall, guarding the space. This is kind of interesting that battery working space needs to be illuminated. So you need light inside. For off-gassing batteries, it needs to be ventilated. And then I just put, tables and appendices at the end, which are kind of useful when you're bending conduit and you're actually an installer. That's something that kind of surprised me about bending conduit, is that there is a minimum radius, and it's really an exact radius. When you bend 1 inch conduit at 90 degrees, it's always gonna to be a specific dimension. So you can't just assume that you can land conduit wherever you want to. If you have to make certain 90-degree bends, you have to do some pre-planning to plan it out.